Now, we will start the tutorial number 3, and the first topic of it would be Pan-Tompkins algorithm. Okay. So, we will use the Pan-Tompkins method for detection of QRS complex using the MATLAB platform, and we will use a simple threshold based method. We know that Pan-Tompkins method has a very sophisticated thresholding technique, which actually requires that multiple pass through the same signal and adaptive thresholding. We will simplify that. We will use a single threshold to detect the QRS complex. Okay. And it is a actually offline procedure, that because we have collected the data and then we are actually running it. So, in that way we would actually do this job, and for that a multiple number of files are given: ECG3, ECG4, ECG5 and ECG6.dat, and each of them they are sampled at a much lower frequency, 200 hertz. That means, we can have the frequency content between 0 to 100 hertz. So, at using that Pan-Tompkins will find the QRS algorithm, and from there we have to find out the average heart rate for the different cases and the QRS width of each of these record. Okay. The average QRS width, that also comes as a good parameter to know that how the QRS complexes are, whether they are normal or not. So, these two we will take. Okay. So, and then we will check that how they are actually appearing with the plots. Okay. So, this is the task, and for that first we have to look at the data. That data is given here in this folder. We get all the data. So, we need to collect them, and we need to collect the MATLAB file to read those data, and we need to keep the input signal and the MATLAB code in the same directory, that is the working directory of the MATLAB. So, with that we start our work, and the first thing would be that we have to read the data to appreciate that how it looks like. So, here first we load the data in a variable named ECG, and then we try to normalize that. So, second and third line, that is for the normalization, first we make them 0 mean. So, we subtract the mean from the ECG signal, we make it 0 mean, and then we are actually dividing it by the maximum absolute value. Okay. So, the ECG signal now it has to be restricted within -1 to +1 after this operation. Next, that we note that what is the sampling frequency, and look at that how many samples are there. S length gives the number of samples in the vector ECG. Okay. And then we create that time index required for the plot, and time index first we write down the sample number, then multiply it with 1 by Fs to get the time instances. Okay. So, that gives us that the plot, that we get the t signal, that the time index, and we use the plot command to get the plot. So, here we see the plot. The plot looks like that we have 20 seconds of data. So, we have shown it for only for here one signal ECG3. The same way we can actually see for all the cases. Next, let us look at the Pan-Tompkins algorithm, that what are the steps in the Pan-Tompkins algorithm. The Pan-Tompkins algorithm, the first step is the band pass filter, okay, followed by a differentiator. Differentiator is to accentuate the QRS complex, which is having the highest frequency in the ECG signal. So, we use the differentiator, which is a high pass filter, to accentuate that, and because the differentiator is actually susceptible to high frequency noise. So, we need to do some filtering before that. So, that is what we are doing here. Why we are doing band pass filtering? That the band pass filtering, first of all, that here if you look at that, this is the frequency axis and this is that this is the amplitude and this is the frequency, then band pass filter is somewhat like this. So, and symmetrically for the real signal, that here also that symmetric component would be there. So, first this region we are actually eliminating to avoid the low frequency artifact, okay, like baseline wandering, and the cutoff frequency here chosen in such a way, it will in the high pass band, it will not only take care of the high frequency noise, it will also eliminate the power frequency noise. So, band pass filter, that is the purpose it serves, then followed by the differentiator, and after that comes the squaring operation. Now, what happens after the squaring? If we take the plot, that we have the value here x and here we take the axis y equal to x square. When we take that square, first of all for the both positive and negative value we will get a here parabolic curve and both will become positive. So, instead of taking absolute value, if we take the squaring operation, that also helps us to get only the positive result. So, after the differentiation we may get the positive and negative values. So, that becomes positive after the squaring operation. At the same time, it has another benefit, that if we look at two values, say here and here, say one maybe say value x 1 and another x 2, such that say x 2 we take k times x 1. So, if we look at that what is the difference between them, compared to that when we take the square, the difference actually increases. Okay. So, that is the beauty of the squaring operation. So, we actually want to get wide separation of the high peaks from the small peaks. So, that is the job also helped by the squaring operation. Next, we look at the moving window filter, that is for low pass filtering, and followed by thresholding, and then we find the R peak. So, these things we will keep on explaining as we move ahead. So, now let us move ahead with the work. First, we find that the band pass filter, in this case the Pan-Tompkins has actually suggested a low pass filter followed by a high pass filter, that gave a band pass filter, and for the numerator we find that these are the coefficients. So, here we have 13 coefficients, and with that, and in the denominator we have 3 coefficients multiplied with 32 means there is a term called 1 by 32, a constant scaling is there. So, to take care of that, that numerator polynomial is multiplied with 32. So, once we have that a and b, the numerator polynomial and the denominator polynomial, then we can create the filter. Here for that we have chosen the direct form 2 filter structure. So, that is the command, that d field dot df2 b comma a provides us the filter in the direct form 2. So, we get the handler of that HD1, and using that we are first performing the low pass filtering. So, we use the command filter, we provide the filter coefficient followed by the signal ECG, and we get the output ECG out 1. Now, ECG out 1, this signal again is normalized, okay, that we take out the mean and divide by the absolute max, so that the signal is contained again in between -1 to +1 and remains 0 mean. So, after that we have to do the high pass filter. So, let us look at the high pass filter. We have the polynomial coefficient b, so it consists of a bigger length -1 followed by 15 zeros, then 32 minus 32, then 14 zeros and 1. Okay. So, we have a big length here. So, 1 plus 15 plus 1 plus 1, that is 18 plus 14, 32 plus 1, 33. So, that is the overall length of the numerator polynomial, and in the denominator we have actually just 2 coefficients, and again 1 by 32 is there, which is actually incorporated as a multiplicand in the denominator filter. And again we choose the direct form 2 structure here, and we get the high pass filter HD2. Okay. So, the HD2, that high pass filter is created, and next that the HD2 filter, it is applied on the output of the low pass filter using the command filter, and we get the ECG out 2, that we can take as the output of the band pass filter consisting of the cascaded, the low pass and the high pass filter. And within this signal, what we get, that the first few coefficients, they have actually that high value, first 40 coefficients. So, they are actually suppressed because of the transient. So, they are suppressed, value is made 1/4, and rest of it that remain the same. Okay. Rest of it remains the same. So, that the first few data, they were unusually high because of transients, they are just suppressed, and then we perform that the operation of that scaling, okay, because it is a high pass filter, that already it is a DC removed signal, the input. So, we are not doing any that the mean subtraction, though if you do that, there is no harm in it. Okay. That is not required. So, that is not applied here. Okay. So, now let us move forward, let us see that how the outputs will look like. So, here we get the, at the top we are getting, this is the signal ECG 3, and below we get the band pass filter output. So, band pass filter output, what we notice that here the compared to the that R value, here was the R, here was the P, here was the Q. Out of that, sorry, that the last one, no, this is not the Q, this one would be the T signal. Okay. So, this T signal is the nearest to the R. Okay. Now, after doing the band pass filtering, we see the difference has increased. Okay. P has got completely subdued. However, the other two things, that Q and S, out of that Q has become more prominent, that is away from the 0 line, I would say, and S is also has become prominent. Okay. So, overall the QRS complex is emphasized by the band pass filter. Here, as the signal, input signal did not have much noise. So, we cannot see that impact, that in terms of the noise removal here in this picture. So, next we look at the derivative operator. The derivative operator is not the simplest form. Here we have 5 that coefficients in the numerator. So, that the 5 coefficient means it is a sophisticated derivative operator. It is doing some along with the derivative some averaging to take care of the high frequency noise, or to make sure that very high frequency noise is not accentuated. And we have a scaling function, that 1 by 8, that we have introduced in the denominator, that we have taken one coefficient multiplied by 8 in the denominator. And again we form that filter HD3 is the filter handler, and we use that the MATLAB function dfield dot df2 for the direct form to that filter, and we provide the B3 and A3, the numerator polynomial and the denominator polynomial for creation of this derivative filter. Now, the next task is to apply the derivative filter here using the filter operation, and the two that the terms we need to give as input to this filter, that one is HD3, that we need to provide that filter, and second, that in the signature, that second variable is the input signal here, that what we get out of the band pass filter, that is ECG underscore out 2. So, at the end of it we get the derivative of the band pass filter here. Okay. And after that we are doing the normalization, and please note that normalization is here only that we are dividing with the maximum absolute value of the output. Again, that we are skipping that part, that we are not subtracting the mean. Again, the reason is that derivative filter itself good enough to remove the DC bias, and our input also did not have the DC component. So, it is doubly sure that no DC component would be there in this signal. So, that is why that part is not actually used. So, here now we get the output of that differentiator filter, and what we notice here, that if we look at a single waveform, here we look at the corresponding output of the difference filter, we see that P and the T wave, okay, this thing has got subdued, that Q or S they have got modified, but they are accentuated. In fact, here the R was bigger S was comparatively smaller. Now, that R and S both have become high. Okay. So, we can say overall the QRS complex has become much more prominent and well separated from the that P and the T wave. But now, what we get that after the differentiation operation, the signal is actually ranging from -1 to nearly +1. So, in that case that we have to use double threshold if we have to separate them out. Okay. So, to avoid that, we go for the next step, we do the squaring operation, and for the squaring operation we are using this command, that dot hat. The meaning of it is that if we have a signal say x with values x1, x2 dot 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 xn. Okay. If it is a, here we have shown a row field vector, it could be a column vector also. Now, if we perform that x dot 2 hat 2, what will happen? It will create actually that element y square. It will create x1 square, x2 square, then x3 square and all, at the end xn square. So, that is exactly what we have performed here, and we have written that output into ECG underscore out 4. And again we normalize it, so that the things are within the bound. So, we normalize it again with the value, with the maximum value. Okay. So, after the normalization, let us see how the image looks like. So, after the normalization of the signal, that here at the top is we are giving the signal after differentiation, and below we are showing that what is the output of the filter. Here we see that after the squaring, first of all it has become positive, that is one good thing. So, one single threshold will do, and what we again see that the small the peaks, they got subdued. Here we see them like small stubs. Okay. So, the difference with the high peak and the low peak, that has actually stretched, and that is another good thing that has happened by squaring. Now, once we do the squaring, one more thing has happened, though both the negative and the positive peaks, they have become positive. If we look carefully, and if we could stretch the signal a single actually cycle at a time, we could see that here that output, it looks like multiple peaks. Okay. So, multiple peaks will make it difficult that to detect. Instead of one, we will get multiple actually values above the threshold. So, then it would be a challenge to find out that which is the location of the R wave, because we know here only one actually R peak is there. So, we need to take care of that situation. So, next thing is to use that moving window integration operation, or moving that averaging MA filter, what we call. So, using that, what we try to do, all these positive peaks we want to merge them together to a single peak which will look like a post. So, here what we have done, or rather let us say the Pan-Tompkins has suggested, rather than we are doing anything, we are just following Pan-Tompkins. Pan-Tompkins has given that we should have a moving average of length 30. Okay. So, we should take the signal last 30 points we should take and do the averaging. So, it is divided by 30. Okay. In fact, for real time implementation you may avoid this point, okay, because later on that scaling is done, it is not a actually offline operation. So, here we are doing the scaling. So, we could avoid this one, but we try to keep the form proposed by Pan-Tompkins. And to do this operation faithfully, we need to pad the signal with zeros in the both the side. We should have 29 more zeros in both the sides of the ECG out 4, and this operation is actually transposed operation. Okay. We had a column vector, we have converted into a row vector and padded both the side with 29 0. So, that when we take the average, we can actually have the output for all the elements corresponding to the that ECG samples. Okay. Otherwise, what will happen? That will go out of range and it will give an error. Now, after this operation at the end, the output what we get, we have again transposed and made a column vector, and again because it is a offline operation, we have this luxury. We are again normalizing it. Had it not been a offline operation, every place where we have used this command, that taking out 0 and normalizing with the maximum, this would not have been possible. Okay. So, now we have the moving average filter. Now, let us appreciate that what is the impact of it. So, at the top we are showing that this was the output of that our ECG signal from what the output we got from the squaring operation, and after MA filter this is what we get. Okay. So, the ragged peaks here, it becomes a post like structure, but one good thing happens that it becomes a single post. So, for each QRS complex we have one post. So, that is the advantage we get here following this step of moving filtering. Now, let us go for the next step. The next step is to threshold the signal, and the thresholding help us to find out the location of the peak. So, what we have done, we have taken, again we take the advantage of the fact that this is the offline operation, we have the signal at hand. So, the threshold TH is taken as the mean of the ECG 5. That means, the signal with the posts, we take the mean value, and next we create a signal of the same length as that ECG signal. The only difference is this is filled with zeros. Next, what we do, that we take out those a vector, the index W, that for which indices that ECG 5, that posts are greater than the threshold value. Okay. And that we note actually here, and this index is used here to write the signal 1. Okay. So, what we do, that means ECG 6 will give 1 when the the post value in ECG 5 is above the chosen threshold. Okay. So, ECG 6 are having value 0 and 1, and now next point is that we would do the differentiation. For that we pad the first value, we add 1 0 here for forward difference, and here also we do it for that end value with 0. That now in the ECG 6 what we will have? We will have signals like this at the location of the posts. Okay. So, the value here is 1, here it would be 0. Now, after the differentiation operation, we are trying to catch that what are the places it is becoming a transition is happening from 0 to 1. Okay. So, we are catching those parts or those indices here in the vector x, and wherever it is becoming 1 to 0, that is marked in, that is caught here and collected in this vector y. Okay. So, once these two are collected, then we know that where the post is starting and post is ending. Next task that is to correct actually the location. Now, so far we have applied number of filters, and out of them the major filters were the low pass and the high pass filter, which has actually that given us the band pass filter. Why I call that they are major? They are major in terms of the delay. That high pass filter of 32 tap, so sorry 33 taps in the numerator, it introduces a delay of 16 samples. The low pass filter having 13 taps in the numerator introduces a delay of 6. Now, how do we get these figures? Because if we have a filter, the midpoint is the center. So, what we get, that this is the amount of delay it has introduced, that is the length of the filter minus 1 divided by 2. Okay. So, by that we get that both the x and the y vectors, they have got a delay of 6 plus 16, that is 22 samples. So, we correct that thing to align the location with the QRS complex. Okay. So, next is we would like to find out the location of R wave first, then we hope you recall that QRS complex, that it looks like this. This is Q, this is R, this is S, and x and y is giving us the bound, okay, within which that peak is lying. So, first we look for the R value. It is done with a simple operation with xi, that is ith peak is located within that xi and yi. So, we find out the maximum value within this range, that is giving us the R peak. Okay. So, that locations they are kept in this vector, that location is kept in R underscore LOC and the value is kept at R underscore value. Now, if we look at, now we are running a for loop to get this actually all the values. Now, after getting this, we need to keep in mind this, especially this location is actually is disturbed. How it is disturbed? That we have calculated the location within a small range between xi to yi. Okay. If the signal has few thousand samples, this could be maybe few tens of samples. So, the location is with respect to that starting from xi. So, we need to, if we have to give it a global location, we need to have that adjustment at that offset along with the location. So, we add xi minus 1 with that location. So, that is how we are getting the location r underscore location I, which will be aligned with the ECG signal. The next task is to find out the q. What we know that q is before r, and we already have found the location of that, and here is x I, and we can say this is r I. Okay. It is within these two. It is the minimum point within the r and the beginning of the QRS complex. So, we find out the minimum in between r location I and r location I minus 8. That means, minus 8 samples maximum difference could be there. Instead of going up to xi, we are limiting the window further, that for the 8 samples, and here we look at this term minus 1, here we are decrementing. That means, that we are starting from, if this is a vector, this is the location I, this is I minus 8, we are starting from here and going this way, okay, and finding out the location here somewhere the minimum is occurring. And the value of the location is kept here, and the value, the q value is kept in q underscore value, and the q location is kept q underscore LOC. Now, again we have to correct it. We have to take care of this with respect to that r location. This is so many samples before. So, we are actually adding 1 minus the q underscore location. Okay. So, we get the q location. Next, we look for the s location, which is again that from I to I plus 10, r location I to I plus 10. That means, that if the r is here, the 10 samples after I that r location we would check to find out the minimum, and we store the value here, s value, and s location keeps that index, but again it is within these 10 samples. So, we need to use the offset, that r location minus 1, we need to add that to find out the location with respect to the original ECG signal. So, all these things it would run in a for loop here, number of times, that how many actually the stamps we have received. So, with that hopefully we could get all the r, q and s points. Next, we would like to actually plot them to visualize that signal. So, how do we do that? First, we use that subplot command, which we are using so many times, to create actually the space, so that we can see the signal more carefully, that side by side we can see the two. First, we with respect to a time we draw the ECG signal divided by the maximum of it, that is normalized signal, okay, because ECG signal is what we have read. So, we have normalized that. If we have already normalized that, we need not have to do that thing. Next, that we show the points that T allocation will give those points or indices where the R point is there and corresponding value is given here, R value. So, we get the x and the y coordinate of the R point, and that is marked with a symbol hat here, and R stands for red. Okay. Next, same way we draw the S values, S location and the S value, and with the help of star, that is designated. Next is Q, the location, time we are getting here, and the value of the Q in y axis we get here, and we use the symbol O to give that location. Okay. And that whole plot, this is limited between 14 to 20 seconds. Okay. The time starts to 0, t starts from 0 to 20. Out of that we are taking only 6 seconds, so that we can get a clear picture of that. Okay. And again in the subplot 2, we are doing the same thing. Here we are showing the full signal. Okay. So, at the top we are taking a part of it, so that we can separate the points Q, R, S, and we can appreciate that. And another thing we have used something called legend, ECG, R and S, that different symbols what we use, that is actually would be given there. So, let us see now that how successful we are in drawing that plot. Okay. So, let us first look at the legend here. ECG drawn with a blue pen, it is given here. R, we have specified that there is a small hat, that they have drawn a small triangle for that. Then S is drawn with a different symbol star, and for Q, O is used. So, that different symbols are used here to designate them separately. And here we are showing that with respect to the signal, we get a nice view that for each of these case, that Q, R, S is nicely picked up, and all of them they are rightly marked. Now, below we are showing it for the whole signal, the 20-second signal, and in this particular case it seems it is successful in getting all of them. Okay. The only problem that here the signal has become cramped. So, we could not differentiate that time location clearly for QRS. Okay. So, this is the whole signal, this is the part of it. So, we get that with Pan-Tompkins, in this case we are successful in getting the QRS locations. Now, we have something more that is left. We need to calculate the QRS duration and the heart rate. Okay. So, for that what we do, we go back in the signal ECG6, which had actually the values. So, what we are looking at, that the first value if it is 0 and second value is 1 or more than that, and next value again is continuing to be 1. That means, we are talking about a jump like this. This value is 0, then 1 followed by 1. Okay. Why we are taking all these things? The first thing is giving the this part is giving a transition, and it should not just come like this and again go to 0. It should be a post to check that the next AND condition is added, that it should have some continuation. So, if it is there, then we increase the count by 1, which was initialized as 0 at the beginning. So, we go through that signal and find out that how many such transitions has happened, and that will help us to give us the count. Next thing, that recall that we have ECG 7, by taking the differentiation here we have added 1 0 at the end, so that after the differentiation we get equal number of samples as the ECG 6. Okay. So, that will give us that the output of the differentiation, and let us see that how we make use of that ECG 7. ECG 7 will have actually, after the differentiation of the signal of looking like this with 0 and 1, it will be consisting of spikes like this, that it will have here 1, it will have here 1 is minus 1, and rest of the place it will be 0. So, we are finding out that where it is more than 0, that means having a transition, and where it is minus 1, that is the starting point of the post and the end of the post in the time. And once we have all those indices, please keep in mind x and y, it is not the single value, but as we have multiple peaks, we are getting all of them. So, we will get 2 vectors. Once we take the difference of these 2 vectors, we get another vector z, which gives the difference between the consecutive, that 2 points, that starting point of the post and the end point of the post. So, we get the width of the corresponding posts in the variable z. Okay. And this value is, we need to keep in mind that we are getting it into that number of samples. So, to get the time or the width of the QRS complex or the post here in time, what we have done, we have calculated the mean and multiplied it with the width of one sample or the intersample interval 1 by Fs. That gives us the duration of the post, and this duration of the post is taken as the width of the QRS complex. Okay. So, here we find out that here we now go for that display, that QRS duration of the ECG 3, that for that we need to convert that number DUR from number to string. It is calculated in terms of seconds, and the count what we got, that is for 20 seconds, to get the number of counts per minute, we need to multiply it with 3 to get the value for estimate the value for 1 minute. So, HT has the count for 1 minute. So, again we use the term number to string to get the heart rate for ECG 3 in terms of beats per minute. So, here we get them in the command window, the corresponding the values. The first one for ECG 3 we get it is 0.193. Second, the corresponding heart rate is 72, that is absolutely normal. For ECG 4, that QRS duration has reduced a bit, 0.18758. Corresponding to that, what is most surprising, that number of beats has increased, it has become 93 beats per minute. For ECG 5, the duration has further decreased 0.16467 second and heart rate is abnormally high, 135 beats per minute. For ECG 6, what we get, the duration has the highest among these ECG signals, it is about 0.2 second, and the heart rate corresponding to that is much lower, it is very low, 54 beats per minute. That means, it is certainly having bradycardia, that unless this person is a sportsman. Okay. So, now let us see that the output in each of these case. This is the first case for ECG 3. First we show the ECG signal at the top, followed by that band pass filter output which suppresses the P and the T wave and also suppresses the noise. Then after taking the derivative operation, we get QRS complex is accentuated. Then after taking that square operation, that output of the derivative has become positive and the difference between the high peaks and the low peak has got reduced or rather accentuated, the separation has increased, but it has number of peaks. So, we have passed it through a MA filter and we get post like structure and clear separation between the small peaks and the high peaks here. Okay. So, here we get very uniform kind of view, that if you look at the post heights, they are more or less same. Okay. So, it is a very nice signal, we could get all the QRS peaks here without any error. So, this is the markings we show, that how we could mark them. This is for that 14 to 20 second, this is for the whole signal of 20 second, that we could get all the Q, R and S points. Next we go for the ECG 4, we show the same set of values, first starting with the signal, then band pass filter output, then output of the derivative filter, then output of the square after the squaring operation, then after the integration. Here we see that the post here is little higher, here they are much lower. So, there is uniformity is not that much. Okay. So, let us see that how successful it would be after the thresholding. We get that here in this case also, that it seems that all the QRS complex Pan-Tompkins algorithm is able to get. So, next we go for the ECG 5 signal. ECG 5, first time we are seeing that baseline wandering. here are the places baseline wandering are very prominent. This portion the baseline wandering is not there so much. Now, after the band pass filter, what we get, that baseline wandering is removed, and here we had a jagged peak, that is giving a high output. After the derivative filter is also highest. So, after the squaring operation, this remains to be the highest one. Here we see all the other QRS complex, it seems to be much lower than that. Okay. So, it is dominating the scene. So, let us see that what would be the impact of it after the thresholding. So, after the thresholding, as that one very high peak was there, that is pulling the threshold above, what has happened that some of the peaks are missed. So, this is one such example, that R wave is missed, okay. R is marked here wrongly. Here another place that R is missed. So, several such misses are there. So, ECG 5 what we get for this one, that this signal, that the Pan-Tompkins algorithm in this form, it could not give a very good result. Again for the ECG 6, the last signal, that is having the low heart rate, we get the signal here, and then we get that the band pass filter output, derivative filter output, the squared output, this is that post we get, and this is the QRS outputs. We get that it is working fine, we get all the QRS complex. Now, we would conclude with our observation, the Pan-Tompkins algorithm is able to detect all the QRS complex in 3 out of 4 signals. Pan-Tompkins algorithm is able to detect QRS wave even in presence of low frequency artifact and irregular occurrence of ECG beats in the signal. Pan-Tompkins algorithm without adaptive filtering fails to detect some QRS wave in ECG 5 due to presence of high frequency artifacts. So, this is the end of the Pan-Tompkins algorithm. Thank you.